And hello, welcome back everyone to this video of von Karman equation. Before I continue, I need to correct three things. Some careless mistakes again. I am very apologetic. So before I continue, let's talk about the careless mistakes. First, it's a partial wrong. The partial derivative is wrong for the mass balance. So if we were to go back and notice over here, when I was trying to do the limit taking process, I kind of, as you can see, this term over here, where my mouse cursor is, it's 1 over delta x, okay? Then you have this integral thingy at rho u x plus delta x and then rho u x, okay? This thing is supposed to become a derivative, okay? But u infinity wasn't part of that derivative, okay? U infinity isn't part of the derivative, so u infinity, I accidentally copied and pasted it here. All right, I accidentally copied and pasted it in here. So this u infinity should be outside the derivative, okay? So that's a careless mistake here. The last term on the right hand side, the u infinity should be on the outside. So yeah, that's one. So yeah, second careless mistake was with Bernoulli's equation. I think I copied it over wrongly. Del p del x equals to rho u infinity del u infinity del x. So that is not correct. There should be a minus sign on either one of these sides, okay? So the Bernoulli's equation, I kind of copied it over wrongly, so do take note of that, okay? So this is Bernoulli's equation, and this is how it's meant to be substituted. So there will be some changes to the derivations, okay? Of course, the u infinity here will be outside, so all of it is corrected, okay? I corrected all of these things, so it should be in the GitHub repository. Just take a look at the heat transfer theory repository under fluid mechanics. You will get you should get it. So let's continue from there. Okay, we have u infinity outside, that's one, and del p del x with the minus. This whole thing will equal to rho u infinity del u infinity del x. So substituting this part here, alright, substituting this part here, you will get the minus sign disappearing. So that's one thing, the minus sign should disappear. Okay, so and then you have your boundary layer thickness on the outside. You divide throughout by the density because they say it's a constant density fluid, and then you will get all of this, all right? Okay, so you divide throughout by rho, you get tau x over rho equals to all of these things. So what were the tricks I used to tidy up the equation? Well, first is using this product rule thing, okay, to replace this side with another expression so that it will fit whatever is on the right hand side. So that's what I kind of did the last video. Though of course just wanted to be extra careful because I was deriving a lot and looking for careless mistakes. So I decided to leave the delta p in a little bit earlier. So this delta p thing is still equals to integral of 1 dy from 0 to delta p is the same. I just made that substitution a little bit later because I was trying to weed out some careless mistakes. But more or less the derivation should be the same. So what I substituted on the left hand side was that delta p u infinity del u infinity del x equals to, well, this product rule expression here. Del by del x u infinity squared delta p minus u infinity del delta p u infinity del x. So all of this will be substituted to the left hand side. Okay, all of this will be substituted on the left hand side. Now once it's there, I start to bring in some things. My delta p equals to the integral of 1 dy from 0 to delta p. So that's why I bring it in. Now number 2, we then combine these things together. Okay. All right. So thus far, this is how the derivation was being done. So before I continue, I just want to make one more note. I think I said in the past few videos that you can swap the order of derivatives and integrals freely. Okay, in general, that's not correct. You should refer to this thing called Leibniz's Rule. Leibniz Rule. You can just search it on Google. So do not, if you want to bring the derivative del by del x into the integral equation, you should be very, very careful to apply Leibniz's Rule correctly. All right. So that's a general thing. Just want to make sure I'm right on that note. So yeah, do not swap it carelessly. Look at Leibniz's rule, and that's how you should swap your integral and differential. What do you call that? Your integral and differential equations. Now, the order of integration and differentiation, especially if you have this kind of expression here. All right. Okay, now I've corrected all those mistakes. Let's just carry on. I spent about 7 minutes talking about careless mistakes, but yeah, it's good because if I kept going on with the careless mistakes, it would have taken like 3 plus 4 videos just to discover where the mistakes were and correct everything. So I saved you all that trouble. Okay, anyway, let's get back to our derivation proper. Let's see. Yeah, I stopped here. Yeah, I stopped here. And that's where we want to continue off from. Okay, so del by del x u infinity square del p minus u infinity del by del x del p u infinity. Now this is just the product rule part. Okay, this is the product rule part. And the terms on the right hand side all stay the same. Okay, all stay the same. Now notice that there is some similarity between the terms on the left and terms on the right. So if you can take a look at the derivatives, del by del x and del by del x here. So these terms have the same coefficient, namely the coefficient of 1. So we can actually combine these two terms into one derivative term. Okay, it's just like packaging. Okay, you just package the terms a bit nicer. So I combine these two terms. So u infinity delta p, u infinity square delta p minus u square. So this is what we have here. You're combining these two terms. Now notice we can also do the same for u infinity del by del x delta p u infinity and this integral term on the right, because the coefficient of the derivative is u infinity. Okay, so this is u infinity. Okay, and u infinity del by del x. Okay, what's positive? Okay, when you add u infinity del by del x integral of u dy, you add this term to both sides, you will have a positive term here on the left hand side, and then delta p u infinity will still be negative. Okay, this integral doesn't cover both of these things. Okay, this integral only covers the first. Okay, so yeah, this integral only covers the first term, not the second term. Just be very, very clear about that. Yeah. Anyway, the dy here should kind of give you that clue. Okay, so now we can replace delta p with the integral of 1 dy and assume that del by del y of u infinity equals 0. This means that u infinity will only change with x if you want to change it. It will not change with this y coordinate. Okay, so yeah, that's the flow assumption that we make. Okay, so given this, we can just bring in the u infinity. All right, this del p. All right, did I? Yeah, I think there's another careless mistake here. this in front of the u infinity, there should be a negative sign. Here should be a positive. So let's change that. Plus and minus. Good thing we go through that. Alright, but other than that, everything else should be the same. I should be able to bring my u infinity into this delta p integral. So because it's a constant, so it doesn't really matter. Okay, and likewise, I can do the same for this term over here. Delta p equals to integral of 1 dy. U infinity square is... Alright, this u infinity square is also constant with respect to y. This u infinity square is also constant with respect to y. If we replace delta p with integral of 1 dy, we can just bring u infinity square in. Okay, and then of course we can just combine these two integrals into one integral because they're the same. And I'm doing the same trick over here. Okay, so these two will be your terms on the left hand side. Now, you notice that this term here is very conveniently in the form of a plus b, a minus b, or a square minus b square. So a square minus b square equals a plus b, a minus b. So we're going to use that expansion on this term over here. This term here, we'll just leave it alone for the time being. Alright, so we'll do the a plus b, a minus b expansion, and this is what we'll get. Okay, u infinity minus u infinity plus u. Whether, I mean, yeah, that's the same thing, yeah? U infinity minus u infinity plus u. Now, one thing we want to do to get our final form of the von Karman equation is to separate out the first integral. So this u times u infinity minus u, this will be one integral, which we will have here. U infinity times u infinity minus u, this will be the second integral. Okay, we separate both these integrals out. Okay, so after separating these two out, so yeah, this whole term here is decomposed into this term here on the left plus this term here on the right. The rightmost term and tau x over rho is not touched at all. Alright, so now we again use product rule to help us with dealing with the last term, so that we can simplify this equation further. Yeah, so that we can simplify this equation further. So what can we do with this last term here? Well, we notice we can use the product rule on the last term, so that we will can combine this term and this term. Okay. Of course, if you use product rule on this term, it will pretty much do the same thing. Yeah. Okay, so if you use product rule on this center term, it will do the same thing. Okay, but I'm using it on the last term here. It's kind of a roundabout method, but it still works out the same way. So this term here, this product rule term, u infinity del by del x, u minus u infinity, this whole integral here. Okay, it is equal to the derivative of this whole term. Okay, u infinity, integral of u minus u infinity dy. This whole thing is differentiated with respect to x, minus del u infinity del x. This whole thing is a differential in itself, and then you multiply it by this integral of u minus u infinity dy. So you see, if you were to rearrange the equation, if you use product rule, this side will be differentiated, this side will be constant, and this is one of these terms here. Then you swap the order around. This u infinity will be constant, and this del by del x, u minus u infinity dy, will be differentiated. Okay, I am not swapping the order of differentiation and integration yet, so this should be swapped with extreme caution using Leibniz's rule, but we are not swapping it at this point. Okay, so we substitute all of this back in. Okay, we substitute this back in, and okay, so this whole term here is substituted wholesale with this expression del by del x, u infinity integral of u minus u infinity dy. so this will appear here. Then minus del u infinity del x, integral of 0 to delta p u minus u infinity dy. So this is this term over here. Okay, this term over here, minus del u infinity del x, then you have this whole integral with respect to y. The rest of the terms, again, they do not change at all. Yeah, they don't change at all. So yeah, almost there. So let me try something. Yeah, so we just substitute this back in. Yeah, I want to do something. And now I want to bring u infinity into the integral here because of course it's constant. Let me have some tools. Yeah, comment, yes. Oh, now it's so much easier. Okay, this is a interesting method. We can bring u infinity into the integral. Okay, so this integral will be brought into u minus u infinity square. No, there's no square there. This u infinity is brought into this integral, and after that we'll just let's see what comes out. The rest of the terms again, keep it constant. So I'm bringing the u infinity term here. Okay. After that, yeah, I want you to notice one thing. Okay, this term and this term, they are negatives of each other. So they are negatives of each other. So yeah, okay, uncomment that. Okay, so look at this. This term and this term are negatives of each other. So you just take out the minus sign and you can cancel off these two terms. They disappear very nicely. Okay, once you do that, your final step is to bring this minus sign in here. Okay, you bring this minus sign in here, so you leave it as a plus on the outside, and these two terms will disappear. And you're pretty much at your final form of von Karman's equation. Alright, you're at your final form. I'll just rearrange it to look like a standard von Karman equation kind of a form. So tau x over rho is on the left hand side. Then you have some of these terms. This del u infinity del x, and then you have this integral here. Then you have del by del x, u times u infinity minus u dy. Alright, all of this here is von Karman's boundary layer equation. Of course, if u infinity is constant with respect to x, this term will disappear. Otherwise, there will be an extra term over here. Okay, these two terms actually are arranged like that for a special reason, and they relate to two sorts of boundary layers. One is the mass deficit boundary layer, and the other is a momentum thickness boundary layer. Okay, but don't worry about that. If we ever come across that, I will explain it a little bit more. The only boundary layer we need to be more concerned about now is the momentum boundary layer, delta p. Okay, but of course, delta p can be replaced by any sort of boundary layer. Does not necessarily have to be momentum boundary layer. But for the purposes of a flat plate flow, and the most simple kind of flat plate flow, the Blasius kind of flow, momentum boundary layer thickness will be the boundary layer of interest to us. Okay, so thanks for watching. We have talked about von Karman's equation. Hopefully it's not too off-putting. I mean, it's way more intuitive than let's say the similarity solution, because there are actual forces you can see and visualize here. However, the potential for careless mistakes are a lot in this von Karman equation, because you keep having to use product rule many times. Okay, and of course a lot of minus signs are around, which makes it easy to make careless mistakes. Very frustrating careless mistakes. Okay, but this is von Karman's equation. Okay, I'll stop for now, and I guess I'll see you guys next time. Thanks again. Bye-bye.